So we're going to continue talking about thermodynamics today, and I always forget this, but I should always open up the last time's lecture. So the last thing that we ended up with, what we ended up with last time was that for an ideal gas made of monoatomic particles in a box, we found that the ideal gas law combined with the kinetic theory of gases tells us that U is equal to, this is the total internal energy, by the way, that U is equal to 3/2 nRT. So this equation tells us a little bit more. It tells us that indeed the total internal energy could be written as 3/2 times capital N KB times T. Remember that NR is equal to NKB. Those two things are related to each other because R is related to Avogadro's number and the Boltzmann constant. And so what we can actually do is we can see how the average energy of a particle is, or we can compute the average energy of a particle, because this tells us that you have n particles, and if each of them have 3/2 kBt units of energy, then you would have this much total energy. And because the energy should be evenly distributed amongst all the particles, this is that equipartition business, which we'll get to in a bit. This is basically that on average, most particles are going to have the same amount of energy. We can actually figure out that we can actually define an energy per particle. So we're going to define, and here I apologize that the font works out this way. We're going to define lowercase u, colon equals, by the way, means define. It's equal to the total energy divided by the number of particles. And this is just the average energy per particle. So in this case, the average energy per particle is just 3/2 times kb times t. So now what can we do with this? Well, this is nice. This tells us how much energy a particle has, but we can go even further, because we know that these are monoatomic gases or monoatomic particles, meaning that it's just a single atom. And so in particular, they're not vibrating or rotating or whatever. So if we know how much energy on average a particle has, we can actually figure out how fast on average a particle is going. And the reason for that is because the energy is just the translational kinetic energy. And so the energy per particle is equal to 1/2, this is from last time, mi times vi squared. This is just the kinetic energy. And so we can calculate an average, quote unquote, average velocity. Now we have to be careful here, because when I say average velocity, what I don't mean is I don't mean just add up all the velocities and divide by the number of particles. And the reason I don't mean that is because if you were to do that, well, velocity is a vector, right? So on average, even though on average they'll all have the same magnitude of velocity, they're all going to be pointing every which way. And actually, on average, the velocity is 0. And a way to see that is that the gas as a whole isn't moving. It's not moving left or right. It's just sitting there bouncing around, whatever. So if the average velocity was not 0, like the average by adding up all of the velocities and dividing by the total number of particles, that would be the same as the center of mass velocity. And that if the center of mass velocity isn't 0, then that means that the whole system is moving. But we're imagining that this box containing a gas is just sitting still. And so we need a different way of computing the average, because the point is you could have two velocities that have the same magnitude but point in opposite directions, and they would contribute nothing to an average. We want to figure out in some way like an average speed. So what we're going to do is we're going to compute the root mean square, the RMS velocity. Now, the RMS velocity is basically exactly as it sounds. You square the quantity. In this case, it's a vector, so squaring it means take the dot product of itself. Then you take the mean, and then you take the square root, root mean square. So the root mean square velocity, also known as VRMS, is just the square root of the average. By the way, if you put something in these angly brackets, that means average. It's also known as the expected value. You take the average of the square of the velocity. And so this fixes the issue for us, because now we're going to compute the square of all of the velocities and then find the average of that. But the square of the velocities doesn't care about direction. It's just a magnitude. So if you have two particles with velocities that are same in magnitude but opposite directions, now the average of the squares would be the same value. So they would just contribute to the average in the way to the average speed in the way you would expect. But now we can go a little bit further, right? So this is the root mean square velocity, or the average speed. But we can manipulate this a little bit to relate this to quantities we already know. In particular, this would be equal to the square root of 2 divided by the mass, where m is the mass of the particle, times the square root of 1/2 m. I just multiplied and divided by 1, times the average of the square. But this quantity here, every particle has the same mass. And so what we're doing is this is actually the average kinetic energy of a particle. So this would be square root 2 over m times the square root of the average kinetic energy. But we already know the average kinetic, actually, let me write it the other way. Let me write it in angle brackets. We already know the average kinetic energy. It's 3/2 times kBt. And so the root mean square velocity is square root 2 over m times the square root of 3/2 times kb times t. Or rewriting it, just so that I can put a box around it, it's equal to the square root of 3 times kb times t divided by m. Now this applies it turns out this applies for all gases. And the reason for this is that, well, the reason will become a little bit more clear later. But the point is regardless of the type of molecule that you have, whether it's a diatomic and it can rotate and vibrate, or triatomic and it can rotate every which way, it has a whole bunch of vibrations. Because the energy is distributed evenly, in particular, it's distributed evenly to its translational kinetic energy. So the translational kinetic energy of any molecule in a gas, at least for an ideal gas, is 3/2 times Boltzmann's constant times the temperature. Now, again, this temperature is in Kelvin. It's an absolute unit, so you have to be careful here. So just to reiterate, this is true for all ideal gases, even though it's not obvious where that comes from. Not just monatomic. And so, in fact, what we actually see is that if you have a mixture of gases, like let's say you have a bunch of helium mixed around with a bunch of argon. They're both monoatomic gases, so that's not going to play a role. But one's heavier than the other. And so we can see that even though they have the same amount of energy, the heavier ones will have less speed, even if they're the same temperature, because the mass of the particles are different. And this makes sense. For a given amount of energy, heavier things move slower. All right, so that finishes this notion. Well, okay, actually, that doesn't. It finishes this kinetic theory of gases, and we're actually going to use the results that we derived here a lot going forward. So keep in mind what we did. What we did last time basically was we used this model of the ideal gas by picturing how the pressure relates to the energy by basically computing things like forces and so on. We use that model in order to understand how the energy relates to the temperature. That same model can also be applied in other situations, but it gets a little bit trickier. So we're going to talk about the equipartition of energy. So equipartition means, well, so what does equi mean? Equi means equal or equivalent. Partition means a way of dividing something. So the equipartition of energy means that the way of dividing energy is equal, kind of literally. So we're going to talk about this, and there's this notion of the equipartition theorem, which we'll talk about in a minute, but I want to give some background. So first of all, I never actually explained where the monoatomic assumption came from when we were doing the previous calculation. Because we did need that. We certainly needed that fact, and the fact that we derived from that monoatomic assumption was that this is 3/2 nRT. Like, where did that come in? Because I stated that as part of an assumption. So it's actually not too hard to think about where it may have come in. So imagine instead a diatomic molecule, meaning it's just a molecule composed of 2 atoms. Well, we could try to repeat the exact same thing that we did before, where we have our molecule. We imagine it's traveling towards our wall at some speed, but then it's going to bounce off the wall. And here's where things get tricky, because you can imagine that it bounces off the wall, and now it's rotating. whereas maybe it wasn't rotating before, or maybe it was rotating and it bounces off the wall in a particular way so that it's not rotating. So before, we had assumed that all of the energy that it initially had was the same as all of the energy that it initially had in the form of translational kinetic energy stayed in the form of translational kinetic energy, i.e. there was no rotational kinetic energy. There was no other type of energy at all. But here, we can't make that assumption. And so the reason why we could make that assumption was because for a monoatomic gas, the rotation is trivial. It doesn't, it's a point. So it doesn't matter how it rotates. And there's nothing for it to vibrate, or there's no potential energy. It just is. So all of its energy is kinetic, translational kinetic. But for a diatomic molecule, now that energy isn't necessarily just in translational kinetic energy. So the energy before the collision would have to be equal to 1/2 times m times v after the collision squared plus 1/2 I omega after the collision. And so we can't just use energy conservation and hence an elastic collision in order to figure out the pressure on the walls and so on. But we can actually handle this issue. We can resolve this without having to redo the calculation and make it a lot more complicated. And the way we do that is by introducing this thing called the equipartition theorem. We also are going to have to introduce a few new concepts, so strap in. So the equipartition theorem, and I'm going to write this out verbatim, is when a certain amount of energy is added to a system like this, and when I say like this, I mean the things are randomly distributed. Like you have a large number of particles, all with random motion and random position and so on. All of the, and here I'm going to introduce a new word, all of the quote unquote modes, you can underline that because it's a new word, that energy can be stored in, or contained in, get an equal share. So before this definition even makes sense, I have to explain what a mode is. So a mode is, you can think of it almost like for a given particle, it's like a bucket to store energy. So for example, there's more than, so for a diatomic molecule, there would be more modes, more buckets to store energy than for a monoatomic particle. And the reason for that is a monoatomic particle can only store energy in the form of kinetic or translational kinetic energy. Whereas for a diatomic particle, it can store energy both as translational kinetic energy, i.e. motion of the center of mass, and rotational kinetic energy. So there has to be some sense, if we're going to use the equipartition theorem in some sort of quantitative sense, i.e. to be able to calculate things and to be able to solve this issue without having to redo the computation each time, we need some sort of way to quantify these. So the question then is how do we track the modes? So I should give you a little bit more of a precise definition of a mode. So a mode is basically the answer, or the number of modes, or how do I want to phrase this? If we were playing Jeopardy, what is a mode would be an answer to the following statement, or I suppose the following question. So let me just write it out. So if we ask the question, which quantities can have energy added to them without affecting other quantities? And so these quantities are the modes. So let me give an example. So the example here for the monoatomic gas would be, well, what is the energy of the whole energy of the system? Well, the energy of the system is 1/2 times mvx squared plus 1/2 times mvy squared. This is for a single particle, by the way, plus 1/2 times mvz squared. And so importantly, you can increase the speed in one direction without changing the speeds in the other directions. And so here, there are 3 modes. In this case, we might call them translational, because they refer to modes associated modes associated with translational kinetic energy. And so the point is, and just to reiterate, because this mode business can be very tricky. If I can add energy, even just in an abstract way, like, is it possible for this thing to change its energy in one way without changing the energies in the other ways? And yes, the answer is if you kick it, say in the z direction, its speed in the x and y directions aren't going to change, but you've still added energy. And so there are 3 different ways that you can do that. You didn't have to choose the x, y, and z coordinates. You could have chosen a different set of coordinates, but the point is there would still always be 3 different ways that you can increase the energy, because there's 3 directions that you can kick it in that don't affect the other directions. And by the way, this notion has already been used. In our previous calculation last time, we used this fact that that the pressure was the same in all 3, or the pressure 1/2, go back and look at the notes, but that the pressure was equal to 1/v times the sum of mi times vix squared, but it was the same for 1/v times the sum of mi times viy squared, and the same for viz squared. These 3 things were independent of each other. And so then we just added them all up and said that, well, now we have 3 of these things that give us the total energy. And so we already used that these 3 things contributed to the total energy equally. That is, that the energy was evenly distributed amongst the 3 modes, because the 3 modes are independent of each other. Like the x, y, and z, they all contribute to the energy in the same way. And so that is, in the case above, we can actually see this explicitly. How many modes does a particle have, or does a monoatomic particle have? It has 3. And how much energy does that monoatomic particle have on average? Well, it has 3/2 times kb times t. So that leads us to conclude that the average energy that each mode of a given particle gets is 1/2 times kb times t. And so now this is the statement of the equipartition theorem. Or rather, this is a quantified statement, or a quantifiable statement. Meaning, so now if we just know how many modes a given particle has, in the case of a monoatomic gas, we know that that particle has 3 modes. Well, each of those modes gets 1/2 times kb times t amount of energy. And so then the amount of energy that that particle has is 3/2 times kb times t. And then we can find the total energy just by multiplying by the number of particles. Now, by the way, there's some additional confusion with naming conventions. Sometimes you'll see people talk about modes, which is what I'm doing, and I'll do the same thing. Sometimes you'll see people talk about degrees of freedom. So technically, these things are different, but from the perspective that you guys have and from the perspective of this course, they're effectively the same thing. So sometimes you'll see someone talking about 3 translational degrees of freedom, or they'll talk about 3 translational kinetic energy modes, and so on. So those are referring to the same thing. Now, I promised that we would resolve the rotational issue. Like, what if you have a more complicated molecule? Well, now that we know how much energy each molecule or each particle gets based off of the number of modes, now we just have to figure out how many modes does it have. So we can also add rotational energy. And this is only to diatomic or larger molecules. by the way, there is a subtlety as to why we don't count rotational energy for the monoatomic gases. And that's basically because it's not quite, but it's basically a quantum effect. Basically, there's, because atoms are not actually things that spin, like they're not like hard balls that can rotate, there is no energy associated with them rotating in that sense. You can't like put a marker down on an atom and ask, well, what direction is it moving in? So that's why that happens here, and that is a quantum phenomenon. Right, so we can add rotational energy to diatomic or larger molecules, meaning like if you have a dumbbell, like if this is your dumbbell, you can rotate it this way, and that certainly does have energy associated with it. And we can do this without changing the translational kinetic energy. And that's because you can have something moving and then start it rotating without changing how it's already moving, right? That's a thing. And so these buckets where we add rotational energy, these buckets are more modes. So the more complicated molecules, diatomic, polyatomic, and so on, those will have more modes than a monoatomic gas. So let's ask the question, how many modes does the diatomic gas have? Well, we know that it's going to have 3 translational modes, 3 translational kinetic energy modes. And that's because just like the monoatomic gas, it can move in the 3 different ways, right? Independently of each other, but it can also rotate. So we have to figure that out. What we're really trying to do is we're asking how many different ways can we add rotational energy without changing the rotational energy associated with the other rotational energies. And you might say, well, how can you have more than one rotational energy? But it's the same thing as the translational kinetic energy. So let's say that we have our diatomic molecule on a set of axes, right? So we have X this way, we have Y this way, and we have Z this way. And let's say our diatomic molecule is currently oriented. This happens every time. It's currently oriented this way, right? So in principle, you could rotate around the x-axis, and the moment of inertia there is not 0, i.e. you can store energy by rotating that way. You guys, like this kind of makes sense, right? It takes effort to actually get this thing spinning this way. And so that means that the energy that you can store there is also not 0. And you can do the same thing with, say, about the z-axis. The moment of inertia about the z-axis isn't 0. And so the rotational kinetic energy about the z-axis also isn't 0, i.e. you can store energy that way. And so in principle, you could just store energy in these 2 ways. You could rotate about the x-axis independently from rotating about the z-axis, and both are different ways to store energy, so that's at least 2 modes. Now the trick here, and what makes diatomic molecules particularly weird, is that the moment of inertia about the y-axis is basically 0. And once you start talking about quantum systems, it just is 0. There is no energy associated with this rotation, for the same reason that there's no energy associated with the rotation of a monoatomic gas. And so here we would say that there is no energy associated with rotating about the y-axis. And so we didn't have to choose this orientation, but regardless of how you orient the diatomic molecule, there will always be one direction that you can't rotate it around, or rather that if you rotate it around, you store no energy, and 2 that you can rotate it around to store energy. And so what this implies is that there are 2 more modes for a diatomic gas than there are for a monoatomic gas. These might be called rotational degrees of freedom. Or rotational modes. So just like I mentioned before, every mode gets 1/2 times kB times T amount of energy. And so if the diatomic gas has, this is on average, of course, like there will occasionally, or there will be some that have more, there will be some that have less, but on average they have that much. So for a rigid diatomic gas, and I'm putting the word rigid in there for a reason, which will become clear in a bit. The energy per particle would be, well, each one gets 1/2 kBt. There are 3 translational modes, 2 rotational modes. So the energy per particle would be 5/2 times kb times t. And hopefully, now you're seeing a pattern. Now we could do the same sort of analysis for a rigid polyatomic gas. Now we have to be careful here. We have to assume that the polyatomic gas has no I equals 0 axis, i.e. it's not just a straight line. So let me just write that down. This is for rigid molecules with no I equals 0 axis. I.e. there's no axis that you could rotate around that has effectively 0 moment of inertia. Those ones get 3 additional modes. And that's because there's now 3 different ways that they can rotate to add energy. And so the end result then is that the energy, this is the total internal energy, capital U, for the different types of gases are as follows. So we have 3/2 nRT for monoatomic gases. So the way we went from 3/2 kBt to 3/2 nRT is we just multiplied, so just as a quick aside, so 3/2 kBt is per particle. So we multiply that by n to get the total number. And then n is equal to the number of moles times Avogadro's number, right? So this becomes 3/2 times n times Na times kb times t. But Na times kb is just r. So that's why it's 3/2 nRT. And the same sort of argument works for the more complicated molecules. So for a diatomic rigid molecule, or rather a rigid diatomic molecule, the energy in the gas of n moles of that gas is 5/2 nRT. And for a rigid polyatomic molecule, I wrote polynomial. I need to fix that in my notes. For a rigid polyatomic molecule, you have 6/2 or 3, but I'm going to write it as 6/2 so you can see the pattern. By the way, generically, when we say polyatomic, we mean some molecule that is not just one long line. We mean the generic molecule. So like think of something like three molecules that are arranged in like a triangle or something. That would be a generic polyatomic molecule. And so we can actually just write more generally. The energy of a gas is n times the number of modes per molecule times 1/2 times kb times t. Or written another way, this is just equal to the number of modes per molecule times 1/2 times n, little n RT. Now this is true for all ideal gases, this n here being the number of moles. So this is really powerful. We went from the kinetic theory of gases and this bizarre equipartition theorem to a really general statement about gases, right? Especially ideal gases. So, and we're going to use this fact, this fact that tells us the total energy of a system a lot. Basically, we now know that for any gas, or for any ideal gas anyway, the temperature and the internal energy are directly proportional to each other, which is a really strong relationship. Okay, so before we continue on to talk more, to start talking about heat capacity again, we have one more thing to talk about, and that's this word rigid. Right, so I didn't actually explain why I put that word rigid. So I'm going to do that now. So we have to talk about vibrational modes. So when we think of a diatomic molecule, you could think of it as just connected by a rigid rod. So you have atom here, and then a rigid rod. They can rotate, they can move, but they're not going to move relative to one another. They'll always stay the same distance away, and so on. But what if we didn't do that? What if we didn't treat the molecules as rigid and we instead allowed them to vibrate? And the reason we might do that, and by the way, this is in our model. So the above calculation for the diatomic molecule was just a model, right? It assumed that the molecules were stationary relative to each other. But in the real world, or at least you might think, that we can treat bonds as if they were springs, or they behave like springs, two springs connecting, or a spring connecting atoms, right? We already made that assumption earlier when we were talking about thermal conductivity. So why can't we do that here? Now, if we were to do that, you would correctly assume, or correctly observe, if you observe this, that, well, once they start moving relative to each other, and this is hard to do, but it's like going back and forth, right? Well, now there's potential energy there, and there's kinetic energy associated with that vibration, right? Like if you have molecules moving around and rotating, but not moving relative to each other, that will be less energy than if they're jiggling back and forth as they move around, right? Because there's energy stored in that oscillation. And so we have to account for that in the mode counting. So the question then is, how many more modes do atoms or do molecules get when we account for the vibration? Now, for a diatomic molecule, it's actually really not that hard to do. But for anything with more than one bond, it gets really complicated. Like imagine, so for a diatomic molecule, there's only really one way it can vibrate. It can vibrate in and out. But for like a triatomic molecule, now like arranged in a triangle, it can vibrate like bigger, smaller, bigger, smaller. It can vibrate like this. It can vibrate in all sorts of ways, and the ways that it vibrates becomes a lot more complicated. Now there is a way to do this. It's by talking about normal modes or eigenmodes, but this is really not something that you're going to talk about, or that you would learn about until like, I want to say like your first year of grad school if you do physics. I mean, you might also see it in you would derive it in your first year of grad school, but like you might see it in like an upper division physics course, or you might see it in like some organic chemistry class or something like that, or inorganic chemistry or something like that. You might see that there, but the true explanation, and it relies on this notion of well, it relies on some complicated classical mechanics. It is complicated. It's not like impossible. It is something that students learn, but it's beyond the scope of this class. So that is just to say, for more than diatomic molecules, this mode counting just becomes unfeasible for us. It's just not easy to do. And it actually depends on the shape too, right? Like if you had a triatomic molecule that had 3 molecules in a row, the ways that it can vibrate will be different than if you have like a triangular molecule, right? Because it depends on the shape and the orientation of those bonds. So you have to know a lot more. But for a diatomic molecule, we can do it. So the energy in an oscillation can be stored in 2 ways. You might say, well, wait a minute, there's only one bond. Well, you're right, but there's 2 types of energy. There's the potential energy, and so you could just imagine you have your 2 particles just sitting there. If you stretch them out, you're going to increase the potential energy. This is related to, effectively, it's related to the length of the bond, but it's not directly related to the length of the bond, but it is related to the length of the bond. And then also there's the kinetic energy of the vibrations, i.e. the relative speed of the particles. And so you could imagine that you increase the speed without changing the potential energy, i.e. if they started off with some speed at this distance, then the energy will be different than if they started off with no speed at this distance, right? So you can change these 2 things independently. Now they'll exchange with one another, but their average values can be changed independently. And so what this means is that for a diatomic molecule, we get 2 more modes associated with this vibrational degree of freedom. These might be, these would be called vibrational degrees of freedom. Now this is where counting starts to get tricky. So if you are going to be doing any Googling for like the homework that's assigned next Oh, is there homework assigned next week? I don't think there can be. I think next week's the exam, right? So there won't be homework assigned on this. But if you were to try to do any Googling on this business, things start to get inconsistent, how people end up counting these things and so on. So no, there's not a homework 6, don't worry. So the point is just keep in mind that the way that we talk about these things varies depending on who you ask. But the idea is still the same. And so with this discussion in hand, we then can establish that diatomic molecules have 7 modes. I'm going to put a question mark there because I just said that they have 5. So that would imply they have 7 modes because they have 3 translational kinetic, 2 rotational, and then 2 vibrational. That would imply that the total energy in a diatomic molecule is 7/2 nRT. And this would be a diatomic molecule with vibration. And this is correct, by the way. If you include the vibration in your model, then this is just true. Now, so the question is like, which one matches reality? And you might say that the one with vibration does because we just left something out last time. Like in the real world, molecules vibrate. But you might actually be wrong. Actually, you will be wrong. So the question then is why did we introduce these rigid molecules in the first place if it's wrong? And the point is, like I just said, it's not wrong. That's actually a more accurate representation of how gases behave at normal temperatures. And now we need to talk about why. So sometimes modes will do this thing where they are quote unquote frozen out. So sometimes it is the case that vibrational modes don't contribute to the energy. Now, this might seem strange, right? Because the equipartition theorem says that, well, any way that you can store energy gets the same amount of energy. So if you can store energy in vibrational modes, then it should get the same amount of energy as the translational modes. But what we're saying here is we're saying that the vibrational modes don't store any energy because they don't contribute to the total energy. So how would that happen? The reason why, and here's where things get unfortunately complicated, the reason why is quantum mechanics. It's another quantum effect. So basically, and here's the basic gist. I can't give too much details on this, but the word quantum in quantum mechanics means discrete. It means, and when I say discrete, I mean like chunks, like little chunks of stuff. You have discrete matter. And so quantum mechanics is basically, the reason it's called that is because energy for certain systems is discretized, i.e. a thing can have 0 energy, or it can have X amount of energy, but it can't have any, or maybe it can have 2X amount of energy or 3X amount of energy, but it can't have any amount of energy between 0 and X, right? And so it turns out for vibrational modes, it doesn't matter. They don't contribute to either because U and U are little u and capital U are proportional to each other. But it was meant to be lowercase u. The vibrational modes, that X amount of energy that they can have, they either have 0 or they have X or they have 2X or 3X or whatever. That X is just too much. The vibrational modes require a certain threshold of energy to turn on. And so if there isn't enough energy being distributed, or if there wouldn't be enough energy being distributed to those modes via the equipartition theorem, like let's say that a vibrational mode needs 2 joules to turn on. Now that's way too big a number, but let's just use that for example. And let's say that the temperature of the system, according to the equipartition theorem, said that the amount of energy each mode gets is 1.5 joules, right? That's not enough. That's not 2 joules, which means that none of the energy can be stored in that vibrational mode. And so that would mean that all of the total energy has to be distributed amongst the other modes because none of it can be stored in the vibrational mode. And so the vibrational mode wouldn't account for any of the total energy. There's just no energy stored there. And so what happens is that the modes turn on, these vibrational modes, they turn on, they activate as temperature increases. And so the point is that, and by the way, this is true for rotational modes as well. Rotational energy is also discretized in this way. But it just turns out that the threshold energy for rotational motion of polyatomic molecules is much, much, much lower than the threshold energy for vibrational modes. And so for most substances that have vibrational modes at all, this temperature of this threshold temperature for vibrational modes is on the order of thousands of Kelvin. So that is to say, you would need to have 1/2 times kb times thousands of Kelvin. That much energy would have to be available to each mode before those vibrational modes start to activate. And so at everyday temperatures that we do in a lab, like, you know, a few hundred Kelvin at most, maybe, or maybe 500 Kelvin at most or whatever for a gas, it just doesn't happen. Those modes just are not active. However, the rotational modes, on the other hand, the threshold for rotational modes is a few tens of Kelvin. And so again, like in a lab environment, you know, your temperature is going to be higher than like 50 Kelvin. 50 Kelvin, remember, is like -220 Celsius. So again, in the lab environment, those rotational modes just behave like any other mode. But the vibrational modes aren't active yet, so we just don't worry about those. So the end result is that for most purposes in this course, we're going to assume that the rigid model, unless stated otherwise. And that's just because we're going to assume we're working with typical lab conditions where we're not at several thousand Kelvin enough to activate those vibrational modes. And so in that case, the rigid model, where they're not able to move relative to each other, is totally valid. It just works because they don't actually vibrate. Because they're not sufficiently hot. Now, with that said, we can go back and talk about heat capacity. I promise this is all going to come together. So we talked about the amount of energy that is in a system of gases. So there's no threshold. Yeah, there is no threshold for translational energy. Yes, that is true. Okay, that's actually not true. The threshold for translational energy actually depends on the size of the box. It depends on the volume. These are basically the quantum mechanics roughly indicates that like what we learned, one of the things we learned from quantum mechanics is that everything is a wave. And so depending on the size of the box, you'll have different standing waves that form in your box. And those standing waves, basically the number of oscillations in that standing wave relate to things like the speed and the position of the particles. And so if your box is so small that you cannot form any standing waves, then yeah, you can't have any translational motion. But that box would have to be like the size of the atom, which is not feasible. It also relates to the temperature, of course. The higher the temperature, the more energy it has, and so the more oscillations there are. So you can fit the oscillations get smaller. But this is just to say that for all practical purposes, there is no threshold for translational motion. Yeah. And that's actually probably principally true, I think, too, because if you put it in a smaller and smaller box, then its energy would have to increase. Yeah, okay, don't worry about it, but yeah, there's no threshold. Right, so we're going to go back to heat capacity. So the reason why we can talk about heat capacity now is we now know exactly how a given gas behaves when you increase its temperature. If you increase its temperature by some amount, we can tell you exactly how much the internal energy increases by. And so that internal energy, that means that can tell us about how much heat you must have added. So we can learn about heat capacity from asking questions about how the internal energy changes. So for what we're about to discuss, we're going to consider an ideal gas in a fixed volume. And the reason why we're doing this, and by the way, yeah, so this is fine. And the reason why we're saying it has a fixed volume is basically because of what we're going to talk about in a bit. We're going to talk about energy conservation. And while the internal energy the change in the internal energy will be equal to the amount of heat you add or subtract from the system. Once you start allowing other ways of energy entering or leaving the system, then that's no longer true. So that's why we want to fix the size of the volume, because we know another way to add or subtract energy from the system, and that's work. Work requires things moving, i.e. like if the box gets bigger, then the average position of the particles move. And so if we just fix the size of the box, then there's going to be no work that could possibly be done, and we'll derive that more rigorously later. And so this implies that the amount of energy that you add is precisely equal to the change in the internal energy. Anyway, with that aside, we can now ask the question, or we can now consider adding a heat to the system. We're going to add an amount Q of heat equal to the system. Now, from the definition of heat capacity, Q is equal to N times C, this is the molar specific heat, or the molar heat capacity, or however you want to call it, times delta T. This is for gases. And we're using the molar one because we're talking about gases here. But if there's no work, as I already mentioned, then the only way that the energy can enter the system is through heat. So that means that the heat is equal to the change in internal energy. But we already know how the change in internal energy relates to change in temperature, right? We saw that for a monoatomic gas, the internal energy was just 3/2 nRT. So the change in the internal energy would be 3/2 nR times the change in temperature. So this would be 3/2 nR delta T for monoatomic gases. Right? So we can then use this expression and this expression to solve for C. 3/2 nR delta T is equal to N C delta T. And so the delta T's cancel, and we're left with that C, and I'm going to put a little subscript here for V. CV, the N's cancel as well, equals 3/2 R. So that little v means that we're treating the volume, or we're imagining that all of this that's happening happens when the volume is constant. The volume's not changing. So that's a constant volume molar specific heat. I don't know why this line went to erase. Now this generalizes easily. Generalizes super easily, actually, because CV is this is the constant volume molar heat capacity. It's just heat capacity with a constant volume, that's all. So this generalizes easily. Easily, not easy. Because we know what the energy is for any type of molecule once we know how many modes it has. For monoatomic gas, it was 3, but for other systems, it would just be however many it has. In that case, the constant volume molar specific heat, or the molar heat capacity, would be 1/2 times R times the number of modes per molecule. By the way, sometimes I will abbreviate the number of modes per molecule as just number of modes. When I do that, note that in most cases, I just mean the number of modes per molecule. So this is our formula. So if we know how many modes a molecule has, this will tell us what the specific heat is. The constant volume molar specific heat is. And so this is kind of remarkable, right? Like before, if you looked up a table of molar specific heats in constant volume, that's you'd have to look for, you'd find just a whole bunch of different numbers, right? And for gases, you'd find numbers that appear in like regular intervals. They're relatively like they have slightly different values, but they're more or less clustered around specific values. And it's these values that they're clustered around. So for example, if you know you're talking about a monoatomic gas, you know the constant volume molar specific heat exactly. Well, not exactly, because these things are, well, for a monoatomic gas, it is basically exact, because those gases are very simple to describe. For a diatomic gas, you just plug in 5, or if it's a hot diatomic gas, you plug in 7. For a triatomic gas, you'd plug in 6, or if it's a hot triatomic gas, then you'd plug in whatever. And so the point is once you know the number of modes, that completely determines the amount of heat it takes to heat up that substance. And that kind of makes sense because the only thing microscopically that could affect the amount of energy it takes to increase its temperature is where that energy goes. Does that energy go towards increasing, how do I want to phrase this? Yeah, basically, if that energy is spread out over more modes, then the average energy per mode will be lower. And we know that the average energy per mode is related to the temperature. So this is just an explicit, easy, simple relationship, which is kind of amazing. So if we had half mono and half diatomic, the number of modes per molecule would be, yes. However, you'd have to make sure that you're counting by, like if you had the same number of moles of each, not like the same mass, because their masses might be different. But yeah. So we can actually use a shorthand for the energy of a system. That the total energy of the system of a gas, of an ideal gas, is N times CV times T. All I did was I plugged in what CV is. And this is just another example of a state equation. It's just a rewriting of one of the old state equations that we had. And this equation applies no matter the type of gas, as long as it's ideal. Actually, well, yeah. I think that this actually just applies even for non-ideal gases. As long as it has a constant volume molar specific heat that doesn't change with temperature, then this is just true. Or that's approximately constant with temperature. So you guys might think like, oh, okay, it's an equation, but this is actually really powerful because it tells us that we can relate the energy in a system, regardless of how it got there. We can relate the energy of the system to its temperature explicitly, just by in terms of measurable quantities. You can just measure CV, number of moles, and the temperature. You can just do that. Kind of amazing. So now let's think about how we use these. So we can use these to study complicated processes. So we're going to slightly change gears here. We're going to talk about thermodynamic processes. And don't worry, we're not leaving behind what we just talked about. But I have a little bit more explaining to do before we can actually use them. This is section 5.7. By the way, at the end of that, like up here, there are going to be there's an example problem that you guys should take a look at. So going forward, we're basically only going to focus on ideal gases, just because non-ideal gases are a lot more complicated. So we can ask the question, what happens when our state changes? Well, when the state changes, that means that the system is undergoing a thermodynamic process. So when I say when the state changes, what that really means is when at least one state variable changes, but it's still the same system. Like maybe you have a system that's in one state. It has this much pressure and that much volume and that many moles of gas, and it's at that temperature. If some of those change, the process that it underwent to go from the first state to the second state is a thermodynamic process. Seems kind of obvious. Now, it turns out that it's hard to study fast processes. At least most of the time. There are some fast processes that we can actually study fairly well, but generally it's hard to study these. And the way to think about these is like an example of a very fast thermodynamic process is you have a hot gas and a cold gas, and then you mix them. They're going to mix very quickly, and that is a hard process to study. Like, just because, well, I don't want to give away the ball game, but it just is very hard, and it boils down basically to solving the Navier-Stokes equation that I mentioned a few lectures ago. So we're not going to do that. We're instead going to study slow problems. And the reason why we're going to do that is because it allows us to take a simplified view. By studying slow problems, we can imagine, or rather we can treat these processes, not problems, processes. slow processes. We can treat these processes as always being in equilibrium, or always passing through equilibrium states. And the reason why we do that, so an example of this, by the way, would be like, rather than just taking a pot and sticking it onto a really hot stove, that's relatively fast. Actually, that's probably sufficiently slow that it's fine. How about like throwing a pot of water into a fire? That's a really fast thermodynamic process because the fire or the water will change phases and heat up very, very quickly. But if you just put your pot of water on a warm stove, but not super, super hot, well, now you're just adding a little bit of energy at a time. And so in between, quote unquote, in between, each time you add a chunk of energy, there will be enough time for that energy to distribute and equilibrate. There will be enough time for that energy to distribute itself amongst the entire system. And so by the time the next chunk of energy has been added, the system will be in a new equilibrium state that has a little bit more energy, but it's still evenly distributed. And so by looking at slower processes, if the processes are sufficiently slow, we can treat them as if they're always stepping between equilibrium states, rather than just jumping from one state to another and passing through a non-equilibrium state. So what we're going to do for us is we are going to study our quasi-static processes. And like I said, these processes are processes that change slowly from equilibrium state to equilibrium state. I.e., if you stop the process at any point, like if you just suddenly stop adding heat, the new place that it will be in equilibrium already. There's also another word on top of the adjective quasi-static. There's another term that's also related, which is the notion of a reversible process. So reversible processes, they basically are as they sound. Reversible processes have to be coaxed. Into happening. I.e., they won't just happen spontaneously. And the reason why is because the reason why we want this, why these would be reversible, is because then you can coax them back into the other direction. You don't have to do a whole lot, but you just have to do a little bit and they'll go the other way. Now, it is true that all reversible processes are quasi-static, but vice versa, but the opposite is not true. But not vice versa. So a difference between a quasi-static and a reverse, or an example of a quasi-static process that is not reversible would be, imagine that you had like, and by the way, these processes can occur for, this would be a good example. Imagine that you had 2 boxes of gas, right? One of them's really hot, or one of them's at a higher temperature than the other. If you put those 2 boxes in contact, they're going to exchange energy relatively slowly. They're going to exchange energy. You know, the hot gas will make its box slightly hotter, and so that slightly hotter box will come into contact with the box of the slightly colder gas, and so it'll transfer that energy, and then that once the box is slightly hot, once the colder gas's box is slightly hotter than the colder gas, then the colder gas will slightly heat up. So basically, they'll slowly transfer energy until they're at the same temperature. But that can't be reversed, because you can't just nudge it a little bit to get it started. It happens on its own, right? You put them in contact, the process begins. It doesn't require any coaxing on your end. And so, and that kind of makes sense. If it'll happen spontaneously, then there's no way to make it go back without doing something to it. So whereas a reversible process would be, for example, you take a gas and you that's just happy on its own, and then you slightly increase the volume. So like imagine you have a gas in a piston. If you slightly raise the piston, the volume will increase just a little bit, and so its pressure and temperature will decrease and so on. And we'll talk about that in a bit. And then you could, and it'll just be happy there. It's happy to do that. It's not spontaneously doing anything. But then you could just push the piston down a little bit, and it'll just happily go back to its old pressure and volume, and it's entirely reversible. So the question then is, how do we mathematically describe these processes? Well, the way that we do that is with things called process diagrams. So by the way, the reason why we're talking about processes is because so far we've talked a lot about the thermo in thermodynamics, but we haven't talked about the dynamics in thermodynamics, i.e. how these things change with time. So a process diagram is basically just a plot of state variables together. So on one axis, you might have one state variable. On another axis, you'll have a different state variable. And the value of those state variables will tell you, so at a point on your plot, like this, think of like an XY plane, a point on your plot will tell you what the pressure is and maybe what the volume is if you plotted pressure versus volume. So for example, well, okay, let me add just a few more words. A point on this plot, or a point on this plot, describes the values of the state variable of a state. Which is just to say we can represent a state as a point in one of these plots. So, or perhaps in more than, if you can plot these things in multiple dimensions, like in 3 or 4 dimensions, then you'd be good, but it's a little bit harder to do that than just 2 dimensions. Come on. I think I'm losing my voice. I sound a little bit raspier right now. So if we were to plot pressure and volume, and we just plopped down a point here, well, that's a point in the pressure volume space, and maybe that point is 4 cubic meters and 30 kilopascals. It's just a point, right? It has 30 kilopascals here, and it has 4 meters here, 4 cubic meters. And then you could do the same plot, or you could do another plot with another set of variables, maybe P and T, right? And maybe it's over here. So, and maybe this one has points 30 kilopascal and 415 Kelvin. So it's possible that these 2 plots, they might correspond to the same state. They don't have to, because they might be describing different systems. You know, maybe one system has 2 moles of a substance and another system has 38 moles. So then they certainly wouldn't necessarily be the same. But we can see that at least the state variables that they share in common have the same pressure, or the state variables that they share in common are equivalent. So they could potentially both of these plots could represent the same state. Now, for ideal gases, the four basic state variables and these 4 state variables, from these 4 state variables, you can derive all of them. Really, actually, you only need 3, but 4 is plenty, right? I'm going to put the word basic here. These are like the fundamental state variables. Are P, V, T, and little n, the number of moles. And so for almost all of the processes that we're going to consider in this class, we're going to consider that the number of particles is fixed. We're not adding more gas or removing gas. So we can just treat n as just some constant that either you have to determine or is determined ahead of time. And then the ideal gas law, given n is fixed, the ideal gas law determines one given the other 2 of these 3. So the point is if you know how many particles there are in your system, just one of these plots, say the PV one, is enough because you know two of them, you know the number of molecules, say n is given, and then you can use the ideal gas law, plug in these values of P and V to solve for the temperature. So this is just saying that we can describe, we can describe an ideal gas like the entire state of the ideal gas with n moles of gas with just a single 2D graph, or a single 2D plot, rather. Because all the other state variables can be derived. You can figure out the temperature if you just plot P and V, and then from the temperature you can find the internal energy and so on. So an example of this would be, let's say that it's the example from before. We have, say, 4 cubic meters and 30 kilopascals, volume and pressure. By the way, these are always in the upper right quadrant because these things are never negative. And let's say that we have, let's just say we have 1 mole. Let's say that's given. Then we can use the ideal gas law and find that 120 kilojoules, cubic meters times kilopascals is kilojoules, equals 1 mole times RT. Now R is 8.3-ish. So this implies that 120 kilojoules divided by 8.31, I should say 120 divided by 8.31 Kelvin equals the temperature, which is, about 30? No, not 30, 15. Yeah, implies that temperature is about 15 Kelvin. Not 15 degrees, 15 Kelvin. And so there's your answer. Like that now you know the temperature, now you could go and calculate the internal energy and so on. It stands for 1,000 kilojoules. The K, oh, no, you're right. That should be 120,000. So this should be 15,000. You're right. Yes, that's really hot. It's a lot hotter than I thought it would have been. Okay, that's fine. It's whatever it is. Oh, but it's at a really high pressure in a relatively small volume, or in a relatively large volume. So yeah, so there's not a whole lot of gas, one mole, but its pressure is very, very high. So for a single mole of gas in that big of a volume, so that means its temperature has to be really, really high. So maybe this was a bad example because this leads to very unphysical numbers, because 15,000 Kelvin is hotter than the surface of the sun. But this is just some random numbers that I pulled out. Now, this is a point. A point describes a state. So what about a sequence of points? Well, it turns out, and maybe this is quite obvious, I don't know, a graph is a continuous sequence of points. Actually, a graph doesn't have to be continuous. It is a sequence of points that transition from one state to another. Equilibrium state. So if we were to plot a graph on our PV diagram, say we had a state at point A, then you had some line connecting point A and point B. Maybe I'm going to put a little arrow here to indicate what direction the process happens in. It goes from A to B. So a graph describes a thermodynamic process. Because this is exactly what we meant by thermodynamic process. It is a transition from state to state. And so in this example, you start off at A, then a fraction of a second later, you're at another equilibrium point. And then a fraction of a second later, you're at another equilibrium point. And you just follow this trajectory of equilibrium points until you get to B. That's exactly what a thermodynamic process is. It's when the state variables are changing. Now, just as a quick note, the processes are not necessarily described as functions, right? They can be, but not necessarily. Remember that like a circle on a graph, like if you were to plot this, That's not a function, right? A function has to pass the vertical line test. Processes can loop back on themselves. They can change direction arbitrarily and so on. So processes are graphs, but they're not necessarily functions, but sometimes they are. Now, here's as a quick note, quasi-static processes must be describable by, or must be depictable by continuous graphs. And the reason for that is because a quasi-static process is one where each increment in time you go to the next nearby equilibrium point. So every time, so if your process jumped, like if you went from A to B and then from B to C, or from A to B, then B to C, then C to D or something. This is just a random example. This part of the process would be quasi-static because you're going from equilibrium point to equilibrium point. But when you jump from B to C, it's not a nearby equilibrium point. You're changing which means that it occurs very quickly because you're changing the variables suddenly rather than changing them incrementally. So that would be a non-static, that would be a non-quasi-static process. And indeed, it's not continuous. Now, these types of diagrams are really handy for computing work. And indeed, they'll turn out to be really handy for computing heat later. Now, you guys might say, well, where did work come from? Well, like I said earlier, work is related to the motion of things. Like when the center of mass of a thing moves, work is potentially done on it, depending on how it moved. So let's go back and think about stuff from 9a. So thinking back to 9a, you know that the work done to go from point A to point B, or from state A to state B, or whatever, is an integral of from A to B of F dot dl. F being the force on the system and dl being the path that the system takes. And this can be rewritten away from vectors as the magnitude of the force times the magnitude of the path length vector times the cosine of the angle between them. You guys hopefully remember that. If you don't, go look at your notes. So then the question is how does this work in thermo? So gases, we know that gases exert pressure, and pressure is just force divided by area. So the question then is how can gas pressure move something? I mean, clearly a force is exerted, but how is that force used? How can it really be considered work? Well, there's a really simple example that we can use to illustrate this. Let's consider a gas in a box sealed by a piston. In a box sealed by a piston. So remember, a piston is like the thing in the engine. It's like a cover that you can slide up and down. So the picture here is you have your box. I'm going to do my best to draw this, but it's not easy. Here's your box with your gas in it. All of the sides are sealed, except the top. Oops. So this thick outline thing, this is our piston. And it's free to move up and down, but it seals the box. So, and let me draw a few more dotted lines. There we go. So imagine that there is a whole bunch of gas below the piston, right? So, and let's assume that the box has length L, side length L. Let's say that the height that the piston is at, let's call it X. And let's say that the piston is going to move up just a little bit of distance dx. Because, so the point is that by putting this piston here, the pressure, like if you just left the piston alone, it would rise because there's pressure being exerted upwards on the box, assuming that there's no pressure exerting downwards from the air. If it was just an isolated environment, then the pressure would push upwards on the piston and it would lift the piston, which would cause the piston to move, right? So that would be work done. And so the question then is how much work is done by this gas at a given pressure, at a given volume, at a given temperature, and so on, when it raises that piston just a little bit. So we know that the pressure or the force on the piston from the gas, well, that's equal to the pressure times the area, right? It's the area of the piston times the pressure exerted on the piston. We're going to assume that the piston moves up by a distance dx. And then at the end of the day, if we want to figure out how much work is done when the piston moves up by some non-infinitesimal distance, then you can just integrate, and that's what we're going to do. So the change in volume of the gas, well, that would just be the area times the change in height, right? Because the area is staying the same. The area is still L squared. The height is increasing by dx, so the volume is changing by the area times dx. Now the work done, small amount of work done because the piston's only moving a little bit, the work done is equal to the pressure times the area, that's the force. By the way, we're just looking at this, but we're looking at the infinitesimal version before you do the integral. So this is force times distance. Now, in this case, the pressure is upward onto the piston because it's uniform. And so the dot product doesn't matter. It's just force times distance. So it's pressure times area, because that's the force, times the distance, dx, that the piston moves. But we can group the a and the dx to get that is the change in volume. So this is to say that a small amount of work done is equal to the pressure times the small amount of change in volume. And so we can find the total work by integrating. The total work is just what we call it W. It is an integral integrating from V1 to V2. We're integrating over different volumes. So you start at volume 1, you end at volume 2. And you're integrating the pressure times the change times the infinitesimal change in volume. Now, this is a really useful equation because we know how pressure relates to things like volume and temperature. In particular, the ideal gas law tells us that PV is equal to nRT. So if all of the other things are constant, then you could just solve for P in terms of those things and then do an integral. But even more useful is that this is the area under a curve. You guys know that an integral is always the area under some curve. In this case, it's the area under a curve on a PV diagram. By the way, PV diagram is what we're calling the diagrams that plot P and V against each other. So we have our PV diagram. We have our point A. We have our process. We have our point B. So the work done is the area under this curve. Where here, this is maybe VA, this is maybe VB. And so the work is VA to VB of P dV. Now you might say, okay, well, how do you do this? Because the pressure clearly isn't constant. How would you find how do you find the area under here? Well, for this random curve, it would be challenging, right? Because you'd have to know the shape of that curve to find the area. But like, what if instead the process was just like straight across? Well, now it's just a rectangle, right? And you can find the area under that really easy. Or what if it was like up and to the right at like a 45-degree angle? Well, again, you can just find the area because it's just like it's a triangle or a trapezoid. So the point is that you can find the total work in two ways. One way is if you know how the pressure relates to the volume and temperature, like if you know, say that the temperature has this profile and the volume has that profile, or the temperature changes with volume in that way and the pressure changes with volume that way and so on. You can use the ideal gas law to write this down. Alternatively, you could just plot the process and then find the area under the curve. They'll give you the same answer. Now, we need to talk about sign conventions again. And I know that you guys probably hate this, but this is sort of important. So the sign conventions that we use this definition of work for gases. And so that implies some sign conventions. In particular, when the gas expands, we assign that to mean that the work is positive. And the way to see that is that if the gas expands, then dV is positive, or then dV is increasing. No, yeah, dV is positive. And the pressure is always positive. So this would be an integral from like, this would be like P times, this would be like P, it'd be like the integral of a positive function from the left to the right. That's always going to be positive. And so the point is that our sign convention tells us that the work is positive when the work is done by the gas via expansion. So the way to think about whether the work is done by or to the gas is think about it this way. When a gas is pushing a piston up, the gas is losing energy in order to push the piston upwards. So we say that the work is positive when the gas does work on the environment, i.e. it adds energy to the environment and loses energy from itself. So the work is done by the gas is also equivalent to the gas expanding. If the gas expands, then the gas loses some amount of energy, or at least it loses the energy that it may have otherwise gained in other ways. So the convention that we use here is that positive work means that the energy of our gas decreases. The convention, and then similarly for negative work, we say that the work is done on the gas. So think about it this way. If you have a balloon filled with gas and you squeeze really hard on it, well, the gas is going to compress, but you're doing work. You're adding energy to the system. You have to push really hard. And so we say that the work is negative when the gas compresses. And so the work is negative when the gas, or when the energy of the gas increases. Now, just as a quick reminder, for heat, it was kind of the opposite. We said that heat was positive when the heat was transferred into the gas. And we said that the heat was negative when the heat was transferred out of the gas. So the sign conventions here are opposite, right? When the energy of a gas increases for heat, that means the heat is positive. When the energy of a gas increases for work, that means that the work is negative. These are opposite signs. Now, just as a quick note, this sign convention for work is the opposite of what you'll see in chemistry. In chemistry, they say that work is positive when it's done on the gas. And they'll say that the work is negative when the gas does work. We use a separate sign convention because we want to use a straight up integral without an additional sign in order to describe work. And this kind of makes sense because we associate increasing volume with positive change, and so an increase in volume should lead to a positive work. At least that's the reasoning here, because we don't want to introduce arbitrary sign changes. So the end result is that we require that the work is negative when the energy on the system done by work is increasing. So you'll have to keep this straight if you've taken chemistry. This is the opposite. This is the system that we're going to use here. If you get it confused, you're likely to screw up problems. So be very, very careful. Right. So we can talk about work and heat just a little bit before we continue. So just as a brief aside, so we know that work and heat only represent transfers of energy, right? And every thermodynamic process is the result of energy either going out or going in, either via work or heat or both. So this is just to say that heat and work cause processes. So these would be called process variables because they are the thing that tell you what the process is. So you can describe a process by saying you have some system with these constraints, you add this much heat, and you take away, or you add this much heat and you let the system do that much work. That will describe a process. And the amount of heat, the amount of heat that a system gains, or the amount of heat that you add or remove from a system, the amount of work that a system does or has done to it, those completely, like those values or the ways that that happens completely determine the process. So with that out of the way, we can actually move on to the first law of thermodynamics. We talked about the 0th law of thermodynamics a while ago. It was either last time or the time before. I think it was it last time? No, it was the time before. So you might think, well, it's been a while since we talked about the laws of thermodynamics, but we're going to get there. So the first law of thermodynamics is literally just conservation of energy. So we've established all of the ways that energy can flow into or out of a thermodynamic system. And so energy can flow into a system or out of a system via heat or via work. So if you have a net energy flowing into the system, then that will tell you how much the energy of that system changes. So in particular, we can write this. Sorry about that. We can write this as the change in the internal energy of the system is equal to the amount of heat you add minus the amount of work that the system or that the gas does. Now here, again, you may have seen this with a plus sign in chemistry. That's because they used a different sign for W. So here we have Q minus W. This equation is the first law of thermodynamics. This is like the Newton's law of, this is like this guy is like the Newton's second law, but for thermodynamics. It's like the big cajone, the big formaggio, other big things. And so the point is that this is literally just a description of energy conservation. We know that delta U goes up if Q is positive. So if Q is positive, our sign conventions tell us that that means that heat is transferred into the gas. So it makes sense. If you add energy to the gas, the internal energy of the gas should increase. Whereas the internal energy decreases if W is positive. But that also makes sense because when W is positive by our sign conventions, that means that the gas is doing work on the environment. So it is losing energy and transferring it out to the environment via work. So the internal energy would decrease. So this is just, it agrees with our sign conventions, and it's just really useful because it allows us to relate the energy of a system, or rather the change in energy of a system, to the heat and the work. And we already know an easy way to compute work. It's just an integral or an area. We already know an easy way to compute changes in internal energy. This is using the equipartition theorem. So we can actually use this often to extract heat, the amount of heat that occurs for a process, or the amount of heat that's exchanged for a process. Now, there's a few interesting and useful facts about this equation. First of all, is that delta U is a change in a state variable, right? So all of the other equations that we've seen for thermodynamics, almost all of the others, like the ones like PV equals nRT, you can write that as a change in a variable, like delta PV equals delta nRT. Like that's totally valid. You can stick deltas in front of both sides. And that relates changes in one state variable to changes in other variables, other state variables. So this equation is unique because it relates the change in a state variable to non-state variables, to process variables, which just says that even though the state variable doesn't depend on how you get there, the route that you take will. So for example, this is just to say that the net change between Q and E, like if you add a bunch of heat, then you'll have to remove some work to get to the same end result. This just says that these three things are intimately connected, even though one of them doesn't care about the process that it's undergoing. It only cares about its state variables. So it's kind of weird and kind of interesting. That's what makes this particular equation very powerful, because you can relate non-state variables to state variables. We can also use this to determine Q from a PV diagram. So if you have a process, you can find the work by finding the area. You can find the change in thermal energy by finding the change in temperature and then relating that to the change in thermal energy by the equipartition theorem. Then you can just add the work and the change in thermal energy to find the heat added. So as a quick example, you have your PV diagram. Let's say you have process here to here. A to B going this way. So the work done, I'm just going to put a W in here because that's the total work done as you go from A to B. And delta U is equal to UB minus UA. And UB is just N times CV times TB minus N times CV times TA. Remember that the thermal energy of the system is just N times CV times its temperature. But we also have that PA, because this is an ideal gas, PA times VA is equal to nRTA. And PB times VB is equal to nRTB. And so we can actually find, TB minus TA, which is what we need in order to find the change in thermal energy. Because we can find TA from one of these equations, TB from the other, plug them in, and then we can find delta U. And then once you have delta U and you have the work done, now you can find Q. So even for processes that are otherwise really complicated, that would have, like, where you wouldn't be able to just write down that Q equals NCV delta T, because, you know, maybe the volume's changing with time or changing with time as the process goes on. You can still find Q just by knowing the work and knowing the change in internal energy. So before we continue and we start, actually, this will probably be a good place to stop now that I think about it. So I'm just going to wax poetic for a minute. So I mentioned before that heat and work are what cause processes to happen, right? So, and I also mentioned that, like, if you want to have a quasi-static process, that means that you need to somehow, like, add very, very tiny chunks of energy. And the reason why you do that, like putting your stove on a low temperature, or putting your pot of water on a low temperature stovetop, the reason why we do that is because we need our system to have time to equilibrate before you add the next chunk. But if you add too much heat, then the system will go out of equilibrium between chunks of energy that you're adding. And so what we really need to do is we need to make sure that the amount of heat that we're adding, or the amount of work that we're letting the gas do, or the amount of work we're doing on the gas, those have to be infinitesimally small. And the reason they have to be infinitesimally small is so that the amount of time it can take to add or to equilibrate is also infinitesimally small. Because we know that, like, if you add a whole bunch of heat to a pot of water, to one side of a pot of water, it'll take time for that heat to distribute. So you have to add just a little bit of energy so that the time it takes to distribute is infinitesimally small as well. So quasi-static processes require infinitesimal changes. Require infinitesimal heats and works that are done. Just so then they can step from one point to its neighbor, right? You don't want to go from here to here immediately. You want to pass through all of the states on the way there. And so another way that you'll often see the first law written is, you might see it written as du equals dq minus dw. And sometimes you'll even have a slash through these d's. This just means that, so the reason why I put a slash is because this is actually a true differential. It's a true very small change. But this isn't like a change in energy, a change in heat, or a change in work. So they put a slash through the d to indicate that it's like an infinitesimal amount of heat that's added, or an infinitesimal amount of work that's done. So you'll occasionally see it written that way. This is just to indicate that if your process obeys this equation, then, or rather, yeah, no, I'll just leave it at that. That this describes how quasi-static processes go from one point to its neighboring point. And with that, I will end lecture here.